These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medium for medical education. If this is the first time you are viewing a program in this optic series, send an email to jyoungmd@gmail.com with your name, position, institution, and city, state, or province, and country. Thanks, and enjoy the podcasts. Today's discussion deals with accommodation. We are going to start out with the idea of accommodation in an emetropic patient. So this is an emetrope who is not accommodating. Zero vergence rays of light are coming in, and they're being focused appropriately on the patient's retina. When an emetropic patient accommodates, he's going to, in essence, overplus his anterior segment. He's going to add in more plus, and he's going to do this in order to compensate for the negative vergence of the rays of light coming in from an object that is at a discrete non-infinite distance from his eye. So we have an object close to this patient's eye. We have a negative vergence coming from the object, and we know that because from the perspective of the patient's cornea, the rays of light converge to the left. That means a negative vergence. Also, they are seen to diverge, also means negative vergence. He's going to accommodate to add plus power to his anterior segment to compensate for this so that the rays of light continue to focus appropriately on his retina. When the patient accommodates maximally, as much as he possibly can, the nearest object that he can see, the nearest plane that he can see, is the near point. We're going to compare this emetropic patient to a myopic and a hyperopic patient. Let's put numbers on this thing. Let's say that this patient is able to accommodate maximally 6 diopters. He's able to add an additional plus 6 onto his anterior segment if he tries really hard. His accommodative amplitude is equal to plus 6. How close is his near point going to be? Where is his near point going to be? It's going to be at 1/6 of a meter from his eye. And we'll contrast this with the idea that we introduced before of the far point. Where's the far point in an emetropic patient? It's at infinity. Let's take the case of a -3 myope. Where is the far point of a -3 myopic patient's eye? If he's -3, it means that the far point is going to be 1/3 of a meter from his eye. Now, that statement's not entirely true, and we're going to discover at the end of this lecture a more precise way to view where the patient's far point is. But let's take it as given that in a -3 myope, that the far point is 1/3 of a meter from his eye. This patient, in essence, is starting out with an anterior segment that's already overplussed by +3. That's why he needs -3 spectacles. We're going to add to this an accommodative amplitude, just like with the last patient, of +6. So he's starting out overplussed by +3. We're adding on an additional +6. What do we get? +3 plus 6 is equal to +9. So this patient's near point is going to be 1/9 of a meter from his eye. The accommodative distance from the far point to the near point in this patient is still 6 diopters, which is his accommodative amplitude. And it is the same dioptric distance as with the first patient, between infinity and 1/6 of a meter. What this means is, without his spectacles on, this patient can see objects clearly that are between 1/3 and 1/9 of a meter from his eye. Beyond that, he can't see. Closer than that, he can't see clearly either. This is a mildly hyperopic patient. In this patient, let's say this is a +2 hyperope. In this patient, his anterior segment is underplussed, because if it had the appropriate plus, the image would focus appropriately on the retina. And he's underplussed by 2. It's the same thing as if we were to take an emmetropic patient and take away 2 diopters of converging power from his eye. So this patient has a deficit of 2 diopters in order to be able to see things clearly at distance. His accommodative amplitude, just like with the last 2 cases, is 6 diopters. However, 2 diopters of that accommodative amplitude has to be used to pay his hyperopic debt. He needs to accommodate 2 diopters just in order to be able to see something at infinity. The 4 diopters that are left over, he can use those for seeing things that are closer. But he needs to first pay his hyperopic debt of 2 diopters. And what he's left with is 4 diopters of accommodative amplitude that can be employed in seeing things closer. So the closest point that he can see, his near point, is going to be 1/4 of a meter from his eye. The accommodative amplitude here is still 6 diopters, and the dioptric distance between his far point and his near point is still 6 diopters. But the patient's experience is that he's able to see things from infinity. Of course, he has to accommodate to see things at infinity, but still he can do it. From infinity to 1/4 meter in front of his eye. The range in real space over which he can see things is from infinity to 1/4 meter in front of his eye, as opposed to the emmetropic patient who is able to see from infinity to 1/6 of a meter, or the myopic patient who could see from 1/3 of a meter to 1/9 of a meter. All of these guys have the same accommodative amplitude. Let's take the case of a very hyperopic patient, let's say a +10 hyperop, who also has an accommodative amplitude of +6. He is not even able to pay his hyperopic debt. He's not able to compensate for the fact that he has a deficit of 10 diopters just in order to see things at distance, to have them appropriately focused on his retina. So he, although he has a far point and a near point, in his experience, he's not able to see things at distance, and he's not able to see things up close. His accommodative range is 0. He doesn't have any range. There's no range over which he can see things in real space clearly without spectacles. Let's just take one last case. This is the case of a +6 hyperopic patient who, like all the other patients, is able to accommodate +6. So if he accommodates maximally, if he really wails on his ciliary muscle, he can compensate just barely for his hyperopia at distance. And he can see things at an infinite distance, but he can't see anything any closer than that. So his accommodative range is from infinity to infinity. I mean, that's about it. That's all he can see. He can't see anything closer. And he gets a wild headache when he does it. In terms of words now, the far point is the point from which rays of light will have a divergence equal to the refractive error of the non-accommodating eye, or the point from which rays of light upon entering the non-accommodating eye will focus upon the retina. The near point is the point from which rays of light upon entering the maximally accommodating eye will focus upon the retina, or the point from which rays of light will have a divergence equal to the refractive error of the maximally accommodating eye. That is to say, the refractive error at distance plus the accommodative amplitude. Accommodative amplitude can be thought of as being the divergence at the far point minus the divergence at the near point. Accommodative range is a description of the patient's experience. So the patient sees things from this distance to that distance. The emmetropic patient in our example was able to see things from infinity to 1/6 of a meter. That's his accommodative range. The myopic patient was able to see things from 1/3 of a meter to 1/6 of a meter. That's his accommodative range. The mild hyperope, the +2 hyperope, was able to see things from infinity to 1/4 of a meter. That's his accommodative range, despite the fact that his far point is in back of the eye. In his experience, he doesn't see things in back of his eye. The furthest he can see is infinity. This is a table like many that you would see in I'm sure lots of textbooks. I just want you to sort of get the gestalt here, which is that the loss of accommodative amplitude over time occurs at different rates at different points in our lives. And I'll let you look over this table or other tables later. I'm not going to spend any more time talking about it here. Up to this point, I hope that I have made everything clear. We've gone in small steps. We've not gotten bogged down with a lot of math. I hope up to this point in the course, things have been abundantly clear. The next topic that we're going to discuss, which is accommodation in the context of ametropia, is complicated and involves math. And I'll bottom line the whole thing right now, which is that myopic patients need accommodate less to see things up close than emetropic patients, even with their spectacles on, and that hyperopic patients need to accommodate more than their emetropic friends to look at objects at the same distance, even with their spectacles on. And we're going to go over why that's true. But before we can do that, we need to revisit the idea of vertex distance. We dealt with vertex distance previously when we spoke about prescribing Bozo spectacles. We're going to deal with vertex distance now, the correcting the refractive error as we move from the spectacle plane, this time to the cornea plane. And this is exactly what we do when we prescribe contact lenses. We're not doing it here to discuss contact lenses, but you would address that problem in the same way. So this is the case of a -3 myope. And I'm defining a -3 myope as someone who requires -3 spectacles. We know that when we correct ametropia, that the secondary focal point of the correcting lens has to correspond in space with the patient's far point. So we're going to kind of work backwards. We know what the correcting lens is that this patient needs. It's a -3 lens at the spectacle plane. We know where the secondary focal point of this lens is. Minus lenses have their secondary focal points on the left. A vergence of -3, or a dioptric power of -3, means that the rays of light converge 1/3 of a meter to the left. So we know that the patient's far point has to be 1/3 of a meter to the left. But to the left of what? It's 1/3 of a meter to the left of the spectacles, not 1/3 of a meter to the left of the patient's cornea. The patient's cornea is an additional 1.2 centimeters to the right of the spectacle plane. So let's work this through. Let's say that we have 0 vergence rays of light coming into this patient's spectacles. They will emerge from the spectacles with a vergence of -3. My question is, what is the vergence of the rays of light not upon exiting the spectacle, but upon hitting the patient's cornea 1.2 centimeters later? The answer to what is the vergence at this point, well, anytime that I ask you what is the vergence, you answer with a question, which is where do the rays of light converge? They converge to the left, so the vergence must be minus, and they converge 1/3 of a meter plus 1.2 centimeters to the left. And I'll let you do the math on your own, but when you do, you'll come up with a vergence at the cornea plane of -2.9. Now, I want you to memorize this number because we're going to be dealing with it later on, that a -3 myope requires a vergence of -2.9 at his corneal plane. Okay, what about the case of a +10 hyperope? I know there was a big anticlimax in that last slide, going from -3 to only -2.9, but I promise you there's going to be more of a difference here because the correcting spectacle is a much higher power. So with a plus 10 hyperope, the secondary focal point of this lens is 1/10 of a meter to the right. We know, therefore, that the patient's far point must be 1/10 of a meter to the right of the spectacle plane, which means that it's in fact closer to the corneal plane. I'll let you do the math on your own to figure out 1/10 of a meter minus 0.012 meters and then 1 over that, and the answer is the power at the vergence at the corneal plane must be plus 11.4. If we were prescribing contact lenses for this patient, we would expect that this patient who needs a plus 10 spectacle at distance would need a plus 11.4 contact lens. Remember that number, the 11.4, because we're going to be using it later on. Okay, let's do accommodation. Let's start out with an emmetropic patient, and this emmetropic patient is looking at an object that's 1/3 of a meter from the spectacle plane. Now, he does not wear spectacles, but I want to kind of standardize these slides. So he's looking at an object that's 1/3 of a meter plus 1.2 centimeters from his cornea. And how much does he need to accommodate? Well, those rays of light strike his cornea with a vergence of minus 2.9. Therefore, he needs to accommodate plus 2.9. We're going to pretend that accommodation takes place at the cornea plane here for the purposes of these slides. So the vergence strikes his cornea, the vergence striking his cornea is minus 2.9. He needs to accommodate plus 2.9 to compensate for it. Let's take the case now of a minus 3 myope, and I know this is a very busy slide. Just stick with it. So this is the minus 3 myope, looking at an object that's 1/3 of a meter from his spectacles. So we know that the vergence of the rays of light striking the spectacles is minus 3. We know that because the object is 1/3 of a meter to the left. These are minus 3 spectacles, therefore we know that the vergence that emerges from the spectacle is minus 6. But it doesn't mean that it's minus 6 striking his cornea. The cornea is 1/6 of a meter plus 1.2 centimeters from this point of convergence. Therefore, the vergence at the cornea plane is equal to minus 5.6. Now, let's work this through. This is a minus 3 myope. We remember from the previous slides that a minus 3 myope has a refractive error at the cornea plane of minus 2.9, not minus 3. A refractive error of minus 2.9 means that his anterior segment is over plus 2.9. So I'm going to say that the vergence that his eye has to deal with accommodation, is equal to plus 2.9, because he's over plus by 2.9, that's what it means to be a minus 3 myope, minus 5.6, because that is the vergence of the rays of light striking his cornea, which is equal to minus 2.7. He has to deal with an extra minus 2.7, therefore he will accommodate plus 2.7 diopters. Plus 2.7 diopters. Contrast this with the emmetropic patient who needed to accommodate 2.9 diopters. So 2.9 for the emmetrope, 2.7 for the myope. And keep in mind, again, this is a myope wearing spectacles. Let's do it for the severely hyperopic patient. And again, the slide is a mess. 1/3 of a meter from the spectacle plane is where our object is. So rays of light hit this spectacle with a vergence of minus 3 and exit the spectacle with a vergence of plus 7. Plus 7 means that the rays of light converge 1/7 of a meter to the right. An additional 1.2 centimeters means that the vergence of the rays of light striking the cornea is equal to plus 7.6. Let's do the math. So it's plus 7.6 minus 11.4, because his refractive error at the cornea plane is minus 11.4. That's why he would need a plus 11.4 contact lens. So plus 7.6 minus 11.4 is equal to minus 3.8. So this patient needs to accommodate plus 3.8 in order to see the object at the same distance. So let's just go over this once more. The myopic patient, all of these guys are looking at an object at the same distance, 1/3 of a meter from the spectacle plane, whether they're wearing glasses in the case of the hyperope or myope, or they're not wearing glasses in the case of the ametrope. The distance is always the same in these examples that I've given you. The ametropic patient will accommodate plus 2.9. The myopic patient, even though he's a mild myope, is going to accommodate plus 2.7, and the high hyperope is going to accommodate plus 3.8. So even with the spectacles on, the ametropic patient accommodates more than the myopic patient and less than the hyperopic patient, even though they're all wearing their appropriate correcting spectacles. This difference drops, of course, when we correct the patients with contact lenses rather than with spectacles, because a myope wearing a myopic contact lens or a hyperope wearing a hyperopic contact lens is a lot more similar to an ametropic patient optically.